Bismillahirrahmanirrahim. Assalamu alaikum and hello to everyone. So in this lecture we are going to discuss about stereoisomerism and its first type, which is geometrical isomerism. In previous lectures what we have discussed is the types of structural isomerism, and in the very first lecture I have told you the concept behind isomerism and its main two types, which were structural isomerism and stereoisomerism. And I've told you that the core difference between structural isomerism and stereoisomerism is that in case of structural isomerism, there is a difference of bond connectivities, right? So the two isomers, they will have different bond connectivities. Whereas in case of stereoisomerism, there will be no difference in the bond connectivities of isomers whatsoever. The only difference between the isomers will be the arrangement of groups in three-dimensional space. And related to that, we have discussed an example about the three chlorocyclohexanol, where I have told you that the two isomers cis and trans can be posed. So I've told you that the cis and trans isomers are stereoisomers and they fall in the category of geometrical isomerism. So this is the topic which we are going to discuss today, geometrical isomerism. It is a type of stereoisomerism. There are main two types which I have told you. That first one is geometrical isomerism and the second one was conformational isomerism. To understand the concept behind geometrical isomerism, you have to understand the concept of rotation of bonds. It is a fundamental concept that single bonds, they are always rotating about their own axis. So what I want to say is, let's say I have a single bonded molecule over here. There is a single bond between two carbons, and there are certain groups attached, and we are naming it arbitrarily as A, B, C, D, E, and F. So what I want to say is that this single bond, it keeps on rotating about its own axis. So it generates like uncountable number of conformers. So what are conformers? Like, let's say it rotates. So what will happen is that let's say we rotate it about 180 degrees. So what will happen is that it will exist in this form. So we have rotated it about 180 degrees. So D will reach here and F will reach here and E will reach here. So you have to imagine. You can take 2 seconds, just pause and try to imagine it in your mind that these groups are rotating. So the sigma bond, it has a rotation about its own axis. So this is what I want you to understand, right? So just take few seconds and imagine that this sigma bond, it always rotates about its own axis. So if you have taken some seconds and try to make it up in your mind that sigma bond is always rotating. The geometrical isomerism, it arises in such cases where there is a restricted rotation about these bonds. So in certain cases, this sigma bond, it cannot rotate about its own axis due to certain complications which we are going to discuss now. So you must understand first and try to imagine it in your mind that sigma bond is always rotating. And then we will discuss that how its rotation can be restricted in certain cases. So what we are going to discuss is restricted rotation. So there are two main cases where there is a restricted rotation about the single bond. The first case is where there is a pi bond, there will be no rotation about there will be no rotation of bond about its own axis. And second case is the cyclic molecules like cyclohexane, cyclopentane. In that case, a single bond, it cannot rotate about its own axis. First, we will discuss that why around a pi bond the rotation is restricted. So we will first discuss the first case, which is pi bond. So to understand this, you have to understand the molecular orbital diagram of this case. Try to recall the concept which you must have studied, that sigma bonds, they are formed by the overlap of by the head-to-head overlap of sigma orbitals, whereas for the formation of pi bond, you must have studied that it requires the parallel p orbitals to overlap, right? So what I'm saying is that now here you see that there is a carbon-carbon double bond. One is a sigma bond and the second one is a pi bond. So for a sigma bond, there is a head-to-head overlap, right? But for a pi bond, there is an unhybridized p orbital. So it has imaginary overlap, like it has just interactions between p orbitals. So this is the basic reason behind the formation of pi bond. There is no physical overlap of orbitals. So now try to imagine that for the formation of pi bond, it is necessary that these two p orbitals, they must align in this way. They must align in a parallel way. So parallel, this word is important. Parallel. So when if there is a rotation of bond, if it occurs, which does not occur in any way. So if it occur, what will happen is that this pi bond, the basic requirement for the formation of pi bond, it will not be fulfilled. So to make it easier for you, I have drawn these certain axes over here. So to understand, you must imagine this in your mind. You can pause the video, you can imagine what I am saying. You can try to like listen two or three lines and then try to imagine. So let's say in first two parts, let's say there is a pi bond. Okay. For a pi bond, what will be the position of two p orbitals, that they will be parallel, right? So there is these interactions. So let's say you somehow rotate this bond, right? It's not possible, but somehow with superpower, you try to rotate this bond. What will happen is that let's say the first p orbital, it reaches y-axis, and the second p orbital, let's say it stays on z-axis, or somehow it goes to x-axis. So now you must know that these three axes, x, y, and z, they are always perpendicular to each other. So now this overlap, it cannot occur, right? This overlap cannot occur because these two p orbitals, they are not parallel to each other. So due to this concept, there will be no rotation when there is a pi bond, right? So just pause and try to understand, imagine and try to understand this concept. If you got this concept, let's move on to the second case of restricted rotation, which is in the case of cyclic compound. Consider an example of cyclopentane. Now, try to imagine that you try to rotate these bonds about their own axis. So what will happen is that the molecules, it will have to go in certain conformations which are extremely unfavorable for its presence, or which are extremely unstable for it. As you know that in case of organic compounds, or in all of the chemistry compounds, they try to stay in certain positions where they are stable, right? So they don't want to go in certain conformations where there is extreme torsional angle or some other steric factors. So those are always unstable for cyclic compounds. So you cannot rotate these single bonds about their own axis in case of cyclic compounds. Now, let's recall what we have studied in the first page, that if there is a single bond, it can rotate, and when other than the cases of restricted rotation, when it is rotating, what will happen is that I told you that if we rotate this molecule about 180-degree, this D has reached here and F has reached here and E has reached here. So now we studied that in certain cases that there will be no rotation of bonds. And the first case is when there is a pi bond. Let's say we have substituents A, B, C, and D over here. If there is no rotation about bonds, so this A, this cannot go there, this D, this cannot go in the place of C. Let's say if there is another isomer of this compound where D is here and C is here. So these two structures, they are completely different structures, right? So in the first case, these two structures, this one and this one, they are same. They both are similar compounds because there is only rotation of bond. But in case of this compound, these two structures, they are not similar because there is no rotation of bond. When there is no rotation of bond, these groups, they will stay in their places. Let's say we have a compound 2-butene over here. In one case, when both CH3 are on the same side, and in another case, when both CH3 are on different sides, these two molecules, they are completely different, right? So such isomerism, which occurs due to the presence of restricted rotation of bonds, such isomerism is called geometrical isomerism. Another name for geometrical isomerism is cis-trans isomerism. So when these two groups of higher priority, they are in same side, we write that this structure is cis 2 butene. Whereas in this case, these two methyl groups, they are on different sides. We say that it is a trans 2 butene. So to conclude, we'll say that isomerism, which arises due to the restricted rotation of bonds. So these groups, they cannot change their places. They will stay where they are. Okay, where they are. So such isomerism is called geometrical isomerism. In next lecture, we'll try to understand the nomenclature, which is the easy nomenclature. In this lecture, I have tried to use different kinds of words to make you understand. So, to understand, you must imagine what is stereochemistry, right? So, when our teacher, they used to teach us this concept of stereochemistry, so they always said that close your eyes and try to imagine molecules in your mind. So, to understand uh, and to make it interesting for you, you must close your eyes and try to imagine these molecules in your mind. So, see you in next video. Allah Hafiz.